Here we learn about L'Hopital's rule. We start off with the simple case, the basic formula, and the case of 0 over 0, and we'll see what that means in a moment. So basically what we have is if f and g are differentiable and f of a equals g of a equals 0, both are 0, and of course g prime of a is not equal to 0, then we have the first form that we see of L'Hopital's rule, and that's this. So the limit as x goes to a of f of x divided by g of x is equal to the derivative of f evaluated at a divided by the derivative of g evaluated at a. Let's see how we can justify this. By local linearity, we know that f and g have these forms. And you might not remember where those come from Calculus 1, but here they are right here. Comes from the limit definition of the derivative. F prime of a is approximately equal to this difference quotient right here. And if you multiply the x minus a over to the left and move the f of a over to the left, you're going to end up with this statement here, and those of course are approximate, and this statement here. And the limit as x goes to a, it's equal. So then we calculate the limit as x goes to a of f of x divided by g of x. We put in those local linearity equivalencies, and then we realize that f of a equals g of a equals 0, so we have a 0 over 0 case, and that's where that terminology came from. So these are just 0, these two here. And then in the limit, as x approaches a, x will never actually be a, so in that case, these two here will cancel out to 1 because x will not be equal to a. And so you'll have the limit as x goes to a of this quotient, and those are just constants, so the limit result is here, and that justifies the theorem. So here's an example. Find this limit here, and we can see that there's trouble, because if x is equal to 1 and we try to plug it in, that'd be sine of 0 is 0 and 1 minus 1 is 0, so we'd have a 0 over 0 case. And we are checking that, so if you plug in 1, you do get 0 for the numerator and 0 for the denominator, and therefore L'Hopital's rule applies. It's a 0 divided by 0 type. So we calculate f prime, and that comes out to be cosine x minus 1, and evaluate that at 1, and we get cosine of 0, which is equal to 1. And g prime is the derivative of x minus 1, which is 1. So g prime of 1 is 1. So L'Hopital's rule says that our original limit is equal to 1. Another example. Log x over x squared minus 1 as x goes to 1. Let's see if that can be done with L'Hopital's rule. We evaluate the numerator at x equal 1, and we get 0 because log of 1 is 0. The exponent you put on e to get 1 is 0. Evaluating into the denominator, 1 squared minus 1 is 0. So it definitely is a 0 over 0 case. We take the derivative of log x, and we get 1 over x. And f prime, therefore the numerator prime evaluated at 1 is equal to 1 over 1, which is 1. The derivative of the denominator is 2x, and evaluating that at 1, we get 2. So here is the result. Applying L'Hopital's rule, it turns out to be 1/2. And I put a graph here noting that as you went toward 1, in this case it's from the right, but in this case it wouldn't make any difference because coming from the right is the same as coming from the left, as the graph indicates. Then your y value there is very close to 1/2, so that justifies the outcome. Now we go on to the more general form, where you have the same case of 0 over 0, but your statement's a little bit more general. It says that f and g are differentiable, that the limit of f divided by g is going to be the limit of the derivatives quotient as x approaches a. So let's see a case of that. When you try to do this limit, let's see if it's a 0 over 0 case first. So f of 0 is sine of 0 plus 7 times 0 squared minus 2 times 0. Yeah, that's 0. And g of 0 is 0 to the 4th plus 2 times 0 is cubed plus 0 squared. That turns out to 0. So it's a 0 over 0 case. So we can apply L'Hopital's. So we take the derivative of the numerator, and we get this numerator, derivative of the denominator, and we get this denominator. But when we go to plug in x equals 0, we still have the 0 over 0 case. So we just apply L'Hopital's rule again, because now we're up here at this case, and we just sort of start over with two new functions. That's a 0 over 0 case. So we take the derivative of this first numerator, and we get this, and derivative of the denominator, and you get this. Now you plug in the 0, and you arrive at 14/2, which is equal to 7. Then I provided a graph out of the TI here, just to show that as x went close to 0, the y values did seem to approach 7. So now you want to see the next video on the worksheet that explains the infinity over infinity case and what happens when x approaches plus or minus infinity. All those cases can be handled by L'Hopital's rule.